Greetings everyone, and welcome back to the bench. It's time to move ahead on the Discrete audio amplifier project, looking at the output stage. Now from the beginning I kind of had an idea of what type of stage I was going to use. However, I decided that it would be good to do a comparison of the Darlington stage and the complementary feedback pair, also called the Z-Cli type configuration, and just set it up on a breadboard and take some distortion measurements and maybe check the stability of the circuits and see how they perform. As I mentioned before, I decided to use the 2SC 5200 and 2SA 1943 output transistors. These transistors are the exact same. These are 5200s here, just in different cases. So in other words, the piece of silicon inside is identical, just put into a different case. They have the exact same specifications, except that this TO220 case is rated for lower power because the pad on the back of these transistors, as you can see here, this is a larger and thicker copper slab that's plated with something, not tinned or whatever they use, and this is smaller, so this has about half the power dissipation. I think this is around 80 watts and this is 150 or 160, something like that. So I'm going to use these because I can plug them into a breadboard and they fit into a socket board easier than these with the fatter legs. Plus these are more expensive, and if I damage them, I'm out almost $3 versus these, which are under $2, so I'll use these since they're the same. Okay, so I have a schematic drawn up. This is the CFP stage we'll look at first. The actual output and driver transistors, emitter resistors, and the charge dissipating resistors, which I talked about in the Darlington and CFP videos. Now I'm just using resistors to bias this. I'm not using a current source. I might end up having to use a bootstrap on both sides for the test. I don't know. I'm not really looking to make an amplifier. I'm mainly looking to test the stability and distortion. And this is biasing. This is the bias spreader circuit. These aren't labeled yet. I have to determine what they're going to be so I can set the bias properly. And the signal goes in here and of course comes out here. I'm going to run this at a lower voltage, plus 10 and minus 10, because I'm using it on a breadboard, and I don't want to have to put a huge heat sink on it. And here is the circuit on the breadboard, sans the heat sink. These capacitors are just supply bypass. I might put some film supply bypass on here as well. Don't have a lot of room for them, but probably will need them. I found these emitter resistors, 0.22 ohm, in the drawer in a lovely shade of pink. Here is the bias spreader and components for that. Of course, the outputs and the drivers. So what I need to do is get a heat sink on this thing and hook it up, and we'll begin some tests. Okay, got it all hooked up here. Found some heat sinks. Yeah, they're kind of small, so I have to watch the power dissipation. If I didn't mention before, there are no stabilizing or compensating components used in this circuit because I just want to see how this is going to perform as it is. Might have to add some, we'll see. But for now I have the power supply set up in serial for plus and minus 10 volts. Current limited at 1 amps, so nothing blows up. Let's turn it on. Looks like It's drawing 10 milliamps, but that just could be this power supply. Well, some current would have to flow because of those biasing resistors. But is the amplifier even conducting? That is the question. What we can do is measure across the bases of the driver transistors and see what the voltage is, because you're going to have about 1.2 volts or so before it conducts. I just threw in a couple 1K resistors here. I don't know what these values will end up being yet. So let's see. See, one side to the other. I have to go from here to here. Tell you what, why don't I put the meter in the shot so you can see what's going on. Okay, anyway, crossed here to here. 0.731 volts. Can't see the decimal point, but that's 0.7. Yeah, that's not going to do it. I'm going to have to adjust the biasing here. Okay, I pulled out the base to collector on the bias spreader. That should have shut this down and caused these transistors to conduct heavily. Didn't do anything, so do I have something wrong? Let's pull this wire out here. Ooh, there it goes. It's shorted out the output. It's at 1 amps, the current limit. So, of course it's in saturation. These are not going to get hot. But let me turn off the supply and evaluate my circuit. Okay, I got this figured out off camera. What I had is the resistor was plugged into the wrong holes, which, you know, I tend to do that often. And once I got it going, it was too difficult to get a close resistor value. You know, keep, you know, searching through my parts here, so I just put in a potentiometer. I found this 2 kilo ohm potentiometer, and I set the bias. Right now I'm running it at, let's see here, it's running at 110 milliamps, which is high. I'm doing that on purpose because I want these transistors to heat up. I want to see how stable this is. Now, here is the bias spreader transistor. It's not in thermal contact, but it's close enough to this heat sink to pick up some heat from it. With a complementary feedback pair type output stage, you're supposed to thermally detect the heat off the driver transistor. But it's, you know, I'm not gonna, I get to run wires and stuff. It just not that easy to hook it up that way without having to solder wires onto the transistor leads and bolt it up against it. I'm not going to do that. Idea is just to see if it's thermally stable. So anyway, so I'm using a 1K here. I might adjust that depending on the sensitivity, and the 2K potentiometer here adjusted to keep the bias where I want it. Now in the actual amplifier, I would recommend putting another resistor in here. That resistor would allow the output stage to go only so high in bias current. Because if somebody gets in there with their screwdriver and starts flipping this around, you can set this to full output. You know, full conduction from positive to negative rail, blow out your output stage. So if you put a resistor in series with the potentiometer and set that to some upper limit, that would limit the adjustability of the current. So you can go from 0 to like 100 milliamps or whatever you want to set that to. So for here, I'm not going to do that though. It's just for playing around. Let's see here. These are warming up a little bit. It's not changing really. I mean, there is some radiated heat. I can feel this transistor is getting a little warm. Not from current going through it, just that it's so close to the heat sink it's picking up some heat. So it's keeping it stable. I'm still playing around with the thermal stability of the circuit. What I did is I turned the bias up to 200 milliamps and turned off the power supply, let everything cool down to room temperature, turned it back on. It started out at 160 milliamps and it's been running for a while. It crept up to 230 milliamps, but it doesn't seem to be running away. It's still a little loose on the thermal stability, I think. But here's the problem. You know, with this layout on the breadboard, I have the drivers really close to the output, so they're going to pick up the heat, and that's going to affect the thermal stability. And also, I don't have very large heat sinks, and that's intentional. You know, thermal stability is also about having the correct size heat sink. These are small heat sinks, are going to heat up pretty quick. Now if I take my fingernail, so I don't, so my finger doesn't take too much heat away from the biasing transistor, if I push that up against the heat sink, see if it drops. Oh, yeah, it's dropping. Look at that, it's dropping like crazy. So yeah, heating up the biasing transistor makes it conduct more and collapse that bias voltage, lowering the the current through the output stage. So yeah, to compensate for the poor layout, I'm putting that transistor closer to the heatsink. I mean, in the actual circuit, when I lay it out, I'm not going to do all these mistakes, but I'm kind of limited with the breadboard here. But I think we're good enough to play with this circuit now. I'm going to set the bias back down to like, I don't know, 25 milliamps or something, and see how it works. Some Black Sabbath, The Wizard, first album, which is a great album. Music player into the preamp, back into the output stage. You have to remember these output stages are all about current. They don't have voltage gain. In fact, output stages with voltage gain are somewhat frowned on today by a lot of the designers, most of them anyway. So the voltage is pretty much limited by what we put in, so it's not real loud or anything right now. So what I'll do is play some tones here, and we'll take a look at the oscilloscope. Okay, so I hooked up my 4 ohm non-inductive load to the amplifier's output, and looks nice and clean. I'll crank it up. And we're getting a little bit of oscillation. You see, we're clipping there. And I believe that is the preamp clipping. I'm giving it all the voltage I can. Let's see. Let me turn down the power supply voltage. We're down at 7 volts, plus minus 7 volts, I should say. Okay, there's that. Now that's the amplifier clipping there. That's at plus minus 6 volts. So let me go back up to 10. So yeah, this is the preamp doing the clipping here. So we got a little bit of instability when the preamp sends it that sharp-edged signal, I guess. To test amplifier stability, one test is to put a capacitor, a small film capacitor, across the output as it's driving a load. So I can plug this 1 nanofarad cap into the output, and there you go. Doesn't like that. Getting all kinds of weird oscillation. It's got a beard. They call it the bottom side fuzzy. When you get that fuzz on the bottom, it's got a weird kind of band of distortion on the top side as well. Let's see what I can do to clear that up. Very high frequency oscillation. Okay, I added what's known as a Bouchereau cell. That's just a series, in this case a 10 ohm resistor and a 0.22 microfarad or a 220 nanofarad capacitor to the output. And we don't see that distortion or the oscillation anymore, do we? So let me now add the 1 nanofarad capacitor. Almost said nano Henry, but we know that's not right. I run out of places to plug that in. It's not oscillating anymore. Okay, now I'm going to go up an order of magnitude and put a 10 nano, I was about to say Henry, 10 nanofarad capacitor across. And look at that. It's oscillating a little bit now. So take it off, put it on, take it off. So yeah, that is making it oscillate. So I wonder if adding the Miller caps on the output, actually on the driver, you put a small value capacitor like 100 picofarads from base to collector. Try it on each side and see if that clears that up. I tried it one in both sides of the amplifier, or the top and bottom transistors. Didn't do anything. You can see it's still oscillating. I think I'll have to resort to an output coil, see if that helps. Okay, now I've put the coil in, and I increased the test capacitor value to 220 nanofarads using a ceramic. Amplifier should not like that at all, but no oscillation at all. I'm curious though, if I remove these Miller capacitors, if it would stay clean. Okay, I removed the capacitors that were across the collector and base on both sides, and kind of like feeding it a square wave, not a really good square wave. But anyway, clean. Should try different signal levels. Little crossover notch, isn't it? We're not running enough current. I gotta adjust that so I can see it. It's hard to tell. Turn that down. Yeah, there's a little crossover notch. Really should be running at a higher bias, I think. See, as I turn the bias down, that's all the way down. See, there's a crossover notch. So I turn the bias up, there it goes away. Problem is I have to stop the signal to be able to read the bias point. I'm actually running it too low. I need to run it about 40 or 50. See how that works. Okay, that's good now. No more crossover notch. Okay, now let me set up my pilot signal. The pilot signal does add a little vibration, you can see, because I'm putting, this is a 1 kilohertz signal and I'm putting a 4.5 kilohertz pilot signal in with it. I want to see the distortion. Wow, that's not too bad really. I mean, this is a no feedback, no global feedback in the circuit. This is a 1% pilot, and the only other actual harmonics is a very small amount, probably like 1/3 of a percent of a second harmonic, and a little notch of 1/3, and some smaller ones. So yeah, without any sort of correction, the amplifier is not too bad really. A couple of things to say before I move on to the Darlington output stage configuration is, well, we're only running about 1.5 watts at this measurement, so not a lot of current. Running more current can make the amplifier do more things. You can't really get a good ground on the breadboard, and it might cause other issues. I'd have to solder together a test circuit and run with that and see how it works. But this video is getting long, and I'm going to call it here. And in the next stage, in the next video, I'll look at a Darlington type emitter follower output stage, and we'll compare notes here and see how they perform. Well, catch you on the next one. 2.48 squared.